Hi everyone, welcome to this online meeting. These strange things that we have to do now to share our results and theorems. And we have prepared this meeting with the help of Luciano Abadias and the Iuma, the Instituto Universitario de Matemáticas and Aplicaciones de la Universidad de Zaragoza. This meeting it's formed by 4 conferences, and the first speaker is Luciano Abadias from the University of Zaragoza, and he's going to speak about some interesting results, which the title I don't remember. So Luciano, when you want.
Okay, thanks, Pedro. Now I'm going to put my presentation. One moment, please. Okay, you can see? Yes, okay. Are you seeing full screen or not, Pedro?
No.
Okay,
no.
A moment.
Yes.
Now it's okay?
No.
It's not full screen, but you can still see your talk.
Yeah, but I think it's not full screen. You can do better. Now, perhaps.
Okay, yeah. In this way, it's okay to see the talk?
You can close the left panel.
Okay.
In any case, we can see it. There is no problem. But there is the markers is on the left panel, and you can close.
I don't see. In my computer, I am seeing.
Control L, Control L. Okay, you can do it in this way if you want. There is not. We can see properly.
Okay.
Don't worry. It's not like.
Okay, I'm going to start. It's a pleasure for me to open this meeting, and I hope that the audience enjoy with the talks in general. Next 20 minutes, I'm going to speaking about some results which appears in a joint work with Pedro Miana, and which are published in a paper of 2018. In that work, we study generalized Cesaro operators on a class of Lebesgue-Sobolev sequence spaces by means of subordination formulas involving C0 semigroups. However, by lack of time, I will only present the results on classical Lebesgue LP spaces. Okay. I have divided the talk into 5 sections. First, I will motivate the problem historically. After that, I will introduce a class of sequence spaces which are contained on LP, and we will see that they are the domain of some generators of particular semigroups that we will present in third section. Okay, such semigroups allow us to represent generalized Cesar operator in 4 sections by means of subordination formula, or also known Hille-Phillips functional calculus for such semigroups. Okay, and finally we saw some pictures about the spectrum of generalized Cesar operator. Well, we start with the introduction. Okay, in the following, F will be denote a complex sequence, and we denote by CF the sequence of its averages. Okay, CF of n is 1 over n plus 1, the sum of j between 0 and n of f of j. Okay, these averages was introduced by Ernest Cesaro in 1890, and the operator that defines is called Cesaro operator. Okay. Well, in 1965, such operator was studied from L2 to L2 by Brown, Halmos, and Seals, and they show that the norm of the operator is 2, and the spectrum is the unit disk centered at the point 1. Okay. This operator can be considered on LP, and the boundedness is a straightforward consequence of the classical Hardy inequality that is given below. Note that this inequality can be written in the following way, where P over P minus 1 is the norm of such operator. Well, note that P is a value greater than 1 and less or equal than infinity. After that, in 1972, Leibniz proved that the spectrum of Cesaro operator on these spaces on LP is the disk centered at Q over 2 of radius Q over 2, where Q is the conjugate exponent of P for P greater than 1. Well, also in 1890, Cesaro introduced the following generalized Cesaro means of any natural order. These averages, or these generalized averages, allow to define the analog generalized Cesaro operator whose boundedness on LP is given by generalized Hardy inequalities. Well, if we take now a complex number beta with real part greater than 0, we can define C beta of F, or C beta applied to F in N, where F is a complex sequence given by this sum. Okay. This expression will be a generalized mean of order beta, and we denote by C beta star the dual operator given by this series, okay, where the coefficients K beta are known as Cesaro numbers, and they are the Fourier coefficients or the function 1 over 1 minus theta to power beta. Okay, these coefficients has the following representation in terms of combinatorial numbers or gamma functions, and they satisfy that the sum of K beta is equal to K beta plus 1. And this is the reason because this operator can be seen as generalized means of order beta. Okay, Stempak in 1994 studied the boundedness of C beta and C beta star on LP spaces, and he proposed to study the spectrum of such operator by means of semigroups, as for example Siskakis did for the classical Cesaro operator on Hardy spaces. Okay, in this talk we face the question proposed by Stempak. First, I'm going to introduce the class of sequence spaces contained in LP. Recall that given a sequence on L1 and a sequence on LP, the convolution belongs to LP for P between 1 and infinity. Well, so if we consider, or if we denote by double B the operator or the minus forward difference operator, double B applied to F in N is F in N minus F in N plus 1. And we denote by D of F in N, N plus 1 times the forward operator. We have that the inverse operator double B minus 1 and D minus 1 is given by this series and this another series. Okay. Well, it's not difficult to see that the operator T minus 1 is injective on LP, and the range of such operator on LP is contained in LP. Okay. The following result states that if we take tau p, the range space given by the range of the operator d-1 on LP, such a space is a Banach space with the norm transferred from the that one on LP. In other words, it's a Banach space with the norm given below. Okay. Now that is an LP norm, where here we take the LP norm of the operator D. D, recall that is n+1 times the operator double B. This is the norm on LP for p less than infinity, and for p equal to infinity, we have the supremum of the operator D applied to F. Well, such spaces satisfy interesting properties. The first one is that, of course, the operator D is an isometry from tau p to LP with inverse operator d-1. Tau p is embedding in LP. We have, as in the case of classical LP spaces, that tau 1 is embedding in tau p, and this last one in tau q, and this another in tau infinity for 1 less than p less than q less than infinity. Also, we have an scalar product that is tau p prime is the dual space of tau p, where the duality is given by the expression here, and p prime is the conjugate exponent of p, where we have that for p equal to 2, we have a Hilbert space with this scalar product, and tau 1 is a Banach algebra with the natural convolution product, and the product between tau 1 and tau p is in tau p. Okay. Now we use these sequence spaces in the following section. First, I'm going to present the following 1 parameter operator families. Take p between 1 and infinity, and f a complex sequence, and t a non-negative real number, and we denote by tau p of t applied to f in n, the operator applying to f in the point n given by this sum, and sp of t applied to f in n given by the series here. Okay. As I have said, we have 2 one-parameter operator family that the following results states that they are contraction C0 semigroups on LP, and whose generator AP and BP are given by the expression below. Okay, AP applied to F in 0 is -1 over P F in 0, and AP applied to F in N is given by this expression where the forward difference appears. Also, BP is similar. And another interesting thing is that the domain of this operator in LP is just the sequence spaces tau p that I have introduced in previous section. Okay. In fact, one can see that such semigroups are not holomorphic on LP. Well, it's easy to see that for each t greater or equal than 0, tau p in t and sp prime in t are dual operator of each other on LP and LP prime, with p and p prime conjugate exponents. And we were able to calculate also some spectral properties of the generator of such semigroups. Okay. First, we have that the point spectrum of the generator AP and BP are the following: the empty set for AP and the half complex plane of real values less than 0 for BP, whenever p is greater than 1 and less than infinity. the empty set for AP also, and the half complex plane of real values of less than 0, union 0 for p equal 1 and the operator BP, sorry. And for p equal to infinity, we have that the point spectrum of AP is equal to 0, and the point spectrum of BP is the half complex plane of real values less or equal than 0 in this case. Finally, also we were able to calculate the whole spectrum of BP, that is the half complex plane with real part less or equal than 0, okay? This is one of the key points of our paper, because it's important to know the spectrum of the generator of a semigroup in order to apply spectrum mapping theorems to calculate the spectrum of the general HSR operators. Okay, because the semigroups are contraction semigroups and the spectrum of BP is this subset, we have that minus BP is a sectorial operator of angle P over 2. Well, we are going now to recall the definition of HSR operators. Recall that for complex numbers beta with real part greater than 0, we had that C beta and C beta star were given by these expressions. The following theorem states that C beta and C beta star are bounded operator on LP, C beta for p greater than 1, and C beta star on LP for p less than infinity. This was proven by Stempak, but we use a more easy expression in order to prove the boundedness, that is the following, okay? Note that we can represent the operators C beta and C beta star by means of a subordination formula, or also known the Hille-Phillips functional calculus of such semigroup, applied to integral functions on 0 infinity. Such integral functions more or less are the function 1 minus the exponential to the power beta minus 1 applied to a short-chain exponential function, okay? Well, this theorem and the next one that says that the HSR operator C beta and C beta star are dual operator of each other on LP and LP prime allow to get the main result on our paper. Such theorem gives us the spectrum of C beta and C beta star on LP. Well, the idea of the proof is the following. First, we get the spectrum of C beta using duality and the spectrum of C beta star. Then the main important steps are to know to calculate the spectrum of C beta star. Okay. The idea is the following. Because of C beta star can be right in terms of the exponential function of the semigroup, no? Because if we have that S is SP of t is a semigroup generated by the operator B, we can see the operator C beta star as the Laplace transform of this function 1 minus the exponential in minus t to the power beta minus 1, and this another exponential function evaluated in the operator B, where B is the generator of S, of the semigroup SP. Well, applying a spectral mapping theorem, if we know the spectrum of the generator, we apply that the spectral mapping theorem, and we get that the spectrum of C beta star, the spectrum of C beta star is the values of the Laplace transform of such function, is this function in zeta, for the values in zeta on the spectrum of the minus generator of the semigroup. Okay, and taking all the values on the half complex plane of real parts greater or equal than 0, we take the range of such function and we get the spectrum of C beta star. Okay, and by duality, as I have commented, we get the spectrum of C beta star. Well, finally, I'm going to show some pictures about the boundary of the spectrum of the operator C beta for different values of P and beta. Well, if we take L2, P equal 2, and several values of beta, for the case of real values of beta, we have the following. For beta 0.5, 1, 2, 3, and 5, we have that the boundary of the spectrum has this form. Okay, note that for beta equal 1, we recover the classical result of Brown, Halmos, and Seals that says that the spectrum of the classical Chesar operator on L2 is the unit disc centered at the point 1. Okay, if we take P equal to 1.5 and bigger values or larger values of beta, we get the following boundaries for the spectrum. And for P equal to infinity, taking several real values of beta, we get the following nice picture. Okay, I'm going to say two notes, two observations. First note, for beta equal to 1, we have that the classical Chesar operator, and we observe in the right side of the picture that we have the unit circle, the circle centered at the point 1/2 and of radius 1/2. And another one thing is that we can observe, or it seems that the envelope of whole boundary of this spectrum seems that it is the unit disk centered at the point 1. Okay, now I'm going to show other pictures for values of beta complex, okay? Complex values of beta. In this case, we take conjugate values of beta, 1 minus I, 1 plus I, and we know that the pictures gives us symmetric curves respect to the real ages. Okay, now taking different values of beta with the same real part, in L2 we get this another nice picture, and only we can take other values of beta. This last one represents different values of beta with the same real part also. On LP for P 1.5, and the last one picture is this another one where I saw different values of beta with different real parts and imaginary parts. Okay, this have seen my presentation. Thank you for your attention, and if you have some question, I'll try to respond you. Okay, thank you so much.
Okay, I give you thanks for the talk, and we have some minutes to do some questions. If someone want to ask something, they can write me in the chat, and I will open the microphone of the people who want to ask you something. Delio.
I have a question. Can you hear me?
Yes.
Do you have more information about the generators? I mean, the spectrum, of course, but also about like their action on some core or something like this?
I think not, because we went directly to the properties that we needed. In that case, the spectrum of we studied that such semigroups are not holomorphic, because our first impression was that one, but we know that this property is not true. And okay, we studied such semigroup on a bigger class on Sobolev sequence spaces, but Pedro, do you remember any more information about such semigroups, or?
We have the feeling that these semigroups are quite good in the sense that I remember that the point spectrum was more or less all the spectrum, the approximated spectrum is the point spectrum, all these kind of things. These semigroups came from the world of the complex variable, where they are very good to work and to do things with this. I don't know for in which direction are you thinking about, which properties of the spectrum, about cones or something like this too, Delio? Which kind of information do you want to know?
No, first of all, I was wondering about like what is the Cauchy problem solved by this semigroup, but also was wondering whether something about like differentiability or so about the semigroup is known. So what kind of, okay, it's not analytic, but can you say something about its regularity?
Yeah. Perhaps some kind of, we try to, the main point is how to apply the spectral mapping theorem. Yes. So we try to get some information, for example, in the holomorphic semigroups, the spectral mapping theorem holds. I don't know if the differentiable semigroups, I think so also, that the spectral mapping theorem holds. Yeah, perhaps we can try to do get more information. It not sounds bad.
Okay, thank you.
Okay, there is also another question of Valentin. I have opened the microphone of Valentin.
Yeah, so can you hear me?
Yes, Valentin.
Yeah, good morning to all.
Good morning for you from Puerto Rico.
It's early here, but yeah. So it's a very nice talk. I had a question. If you would go to the representation of the operator C beta.
Sorry, the representation of C beta?
Yeah, the formula that defines C beta.
You can see? Do you want to see?
Yeah, if you can post it. Yeah.
I'm going to share my one moment, please. Can you see that?
Yeah, okay, so here you have the K beta is the kernel that comes from, that was previously defined, yeah? So my question is, suppose you take, you replace K beta, this kernel, yeah?
Yeah.
If you can replace by some other, if you replace it by some other sequence, some other sequence depending on beta, yeah?
Yeah.
So what kind of results can be obtained in terms of?
Yes, I suppose that if you see the talk in a general point of view, you see that C beta is a generalized a generalized mean, okay, where K beta are the Fourier coefficients of a particular holomorphic function on the unities, okay? If you take, I think that if you take another holomorphic function, okay, in the unit disk, and you put where is K beta, such Fourier coefficients, and 1 over the sum of these Fourier coefficients, I think that you have an operator, okay? Yes. And I'm sure that there will be, or under some assumptions, there will be a relationship between such operator C beta, maybe, and if you put here an integrable function on 0 infinity, and if you put here the semigroup. Maybe it could be a thing to study.
Okay, thank you.
This was your question, more or less, or no, Valentin?
Yeah, the question was, yeah, I think you answered the question. That is,
Okay.
if one would replace the K beta here by some other sequence and see what can be achieved.
Yes.
Yeah. It is connected, the kernel key beta with this Cesar operator, but if you replace the kernel, here perhaps it will be appear another function and you will appear another operator. Yeah, it could be work. Yeah.
Okay.
I don't know if there is more question. If not, we thanks to Luciano this nice talk. And
thank you so much.
The next speaker is Delio Mugnolo from the university, FernUniversität in Hagen. I met with Delio, I don't know, 20 years ago or something more than when we were both students. He was in Ul or in in Ul,
even in Bari.
In Bari also. Wow. In so many congress when we spend very nice days, short time and drinking beer and okay, no more. I have to. He want to speak about the spectral partition of quantum graphs. Okay, so as you want, Delio.
So thank Luciano, thank Pedro for this invitation. I'm very happy to be here. I mean, I visited Pedro once in Zaragoza, and it was a great time. So actually, I really wish this could happen again anytime soon. But for the time being, I think it's a very good thing that we also organize this kind of meetings. And there is one good thing about this situation is that I think the exchanges not only between North America and Europe, but also between Europe and Asia, they are greatly boosted. So I think it's great that we all can be here and the Sashi also is here. Anyway, let me share my screen. No, sorry. So do you see my screen now?
Yes, we see.
Yes.
Okay.
Perfectly.
Okay. So what I'm going to talk about today is some work which is being performed over the last, I think, 5 years already. So it's a long-time project. It all started at a time when James Kennedy from, now he's in Lisbon, and Pavel Kursov from Stockholm, we were organizing some research project in Bielefeld in Germany. And we heard about a theory I'm going to present soon about spectral partitions of domains, and we thought we could do something similar on graphs, which was our common topic. And then we learned, or James actually learned, that Corentin Lénard from France had some nice results about this theory, and then we invited him to join us. And then we started some research, and actually we finally completed our paper last year. And in fact, this paper, this is the basic thing I'm going to talk about today, just got accepted in last days in calculus operations of partial differential equations. And then there was a follow-up of this article, which James and myself were started preparing together with our PhD students, Matthias Hoffmann in Lisbon and Marvin Plümer in Hagen. So these two articles are the basis of my talk today. Okay, so I mean, you see the topics are spectral partitions of whatever, of quantum graphs. I will introduce quantum graphs later on if you don't know it. But first of all, what's a spectral partition of something? Okay, so let me present some history. So can you see this screen too, right?
Yes, we see.
Okay, very good. Okay, so everything starts with the idea of partitioning a domain, a planar domain, into two subsets. And the question is, of course, you can just do this however you want. You can just take some scissors and cut something into two, but the point is, of course, to whether there is any reasonable way to do so. I mean, like having special homogeneity in this cut, so to say. And there is a classical approach, which is very old. The idea is maybe we can use eigenfunctions to do so. So the point is maybe we can consider smooth functions of a certain domain omega, and then cut this domain where the eigenfunctions are very steep gradient. And the reason for this is, first of all, because it works well in many situations. And the second has been pointed out by Jeff Cheek at the end of the 60s, beginning of the 70s. He realized that this is also related to a rational problem, to a non-variational problem of cutting along small lines, and in such a way that the two subdomains that arise are more or less the same size. So you penalize the size of the boundary and try to make this two new subdomains as similar as possible, or as same volume, as close volume as possible. Okay, so this has been a very successful approach in the case of subdivision into two subsets. There are a lot of variants and tune findings and whatever. But of course, there is a very natural question: what happens if you want to partition your domain not into two subsets, but maybe into k subsets? And well, because this two partitioning was sufficient with this nodal approach, maybe one could come up with the idea of applying the same technique and also use k eigenfunctions to partition a domain into k subsets. Okay, so let's say the k eigenfunction has new k nodal domains. Okay, if you are in one dimension, so if you're trying to cut an interval into k pieces, this idea is perfectly fine. So Sturm in the 1830s proved his famous oscillation theorem, and he showed that the kth eigenfunction of an interval, of the Laplacian of an interval, has exactly k nodal domain. So far so good. Almost 100 years went by, and Cour in the 1920s, he wondered what happens for higher dimension, and he proved that in general, for higher dimension, this approach is not necessarily guaranteed to work, because you only have you have at most k nodal domains, but it could be less. So okay, so maybe I should be more precise. So just in case you were wondering, a nodal domain is a subdomain of a domain where an eigenfunction is either positive or negative. So even in higher dimension, we know that the size of the lines where the eigenfunction attains value 0 is negligible. So basically, the whole domain is made up by pieces where the eigenfunction is either positive or negative. So you just take the connected components of this pattern, or this something called a Chladni figure, and then you try to use them to partition your domain. So once again, in one dimension, everything works, but in higher dimension, this is not necessarily the case. You could have come up with less subdomains than you wish for. So this could happen, and the point is that actually this will happen, because Pleyel proved in the 1950s a very famous theorem for the Laplacian with Dirichlet boundary conditions. So this is typically the case you are considering, and Corentin-Lénard extended this for Neumann and Robin boundary conditions a couple of years ago. So what Pleyel showed is that not only it could happen that a kth eigenfunction has less than k nodal domains, he proved that in fact only finitely many eigenfunctions will have k nodal domains, because the sequence nu k over k will typically converge towards something like 2/3 more or less. So you are far away from being close to 1. Okay, I was, just for the sake of completeness, I also had a couple of references. So Jean Bourgain, a couple of years before passing away, proved by very refined methods, which were further refined by Stefan Steinerberger, that actually can even improve a tiny bit this estimate. And at the moment, so a lot of people's guess is that Polterov's conjecture holds. So in fact, one guess is that this lim sup of this sequence should be 2/pi, whatever. Anyway, the point of this 2/pi or 2/3 or whatever is that you're far away from being close to 1. So there is really no reason why nodal domain partitioning should work if you really are interested into having k subdomains. Okay, this is nice and good for domains, but the field where this is really very important, interesting, is data science and graph theory, for reasons you can imagine. So basically, you have a data set. This is just a cloud of points, and then you connect them with each other depending on the closeness or the proximity due to empiric measures I don't want to go into. So you create a graph, and then the question is, how can you get k clusters out of this graph? So you're interested of not just cutting into 2. This would be possible and feasible by known methods, but into k. So once again, new k. Okay, there are some technical problems because unlike in the case of domains, it could be that on a significant part of your graph, the eigenfunction vanished. But if you fix the definition of nodal domain a correct way, then you can still come up with a meaningful theory. So we denote again by new k the number of nodal domains, and then you wonder how many. The question is how many nodal domains exist. And okay, so Miroslav Fidler in the 70s, he proved that you actually have exactly 2 nodal domains for the second eigenfunction. The first eigenfunction for the discrete Laplacian will be just the constants. The next one will change sign, and then in fact you will have just 2 connected components of this nodal partition. So everything is fine for 2. What happens for higher k? Then one had to wait almost 25 years or more than 25 years. But then Brian Davis and his co-authors showed that in general you only have new k is less or equal than k. So this is pretty much what Courant proved for domains. And in fact, you can, I mean, now certain estimates are known for this new case. So it is known that, so Gregory Bercolayco showed that for trees, you actually have equality of this estimate. But in general, you only have that, that the lim sup of the sequence new k over k is equal to 1. Fine. So in principle, unlike for domains, this choice would still be feasible. This ansatz would still be feasible. And in fact, there was a very important, very famous paper by Lee, Vescaran, and Trevisan from 10 years ago when they showed that this so-called multi-Cheeger partitioning problem is well posed. So you can actually use nodal domains to k-partition a graph under certain geometric condition that can be coded into spectrum. So basically, if k eigenvalues are close to 0 of your discrete Laplacian, then you have good chances to have a meaningful k partition. So this is the more or less the state of the art till 10 years ago. But then there was a nice paper appearing again in some computer science journal 2014 by Austin White and Woody. And they propose a completely different way of partitioning data points or graphs based on so-called spectral minimal energy. I don't want to go into their findings, but I want to go into this method, which is actually the topic of this talk. So what is a spectral minimal energy? So in fact, Austin White and Woody did not invent this method. This was invented 10 years before by a group of Italian mathematicians. So the idea is the following. So once again, you want to partition a domain omega into k open, and okay, it's really meaningful to assume that they are also connected, of course, mutually disjoint, and of course non-empty subdomains omega, small omega 1 to omega k. So the idea that this Italian mathematician, so Conti, Terracini, and Verzini had was the following. You could just introduce following functionals. So capital lambda k infinity should measure the maximum of the first Laplace eigenvalue of the Laplacian restricted to this subdomains omega I. So you take your omega, you partition it into k different pieces. Each of these pieces supports Dirichlet Laplacian. Then you compute the first eigenvalue on this omega, domain omega 1, then omega 2, and omega 3, and so on. And then you compare all of them, take the maximum, and this will give you a functional lambda k infinity. So this guy is not very smooth. So these people decided to introduce also a family of smoother functional they called lambda k kp, which basically instead of taking the maximum of the sequence, take the the p norm or the p mean of this sequence. Okay, this so let's perform a first plausibility check. Does this method at least work well for k equal to 2? So if you want to partition your domain into 2. And this is in fact the case because they showed right away that the minimum, so this guy is of course bounded from below because it's positive valued. So it has an infimum, but does it also have a minimum? Yes, it does. The minimum in the case of k equal to 2 is exactly given by the second Laplace eigenvalue. So everything works fine. And in fact, the nodal domain of the Dirichlet Laplacian, so the domain where the first sign change in eigenvalue is positive and the part where it's negative, they form not only a nodal domain, but also a minimal partitioning with respect to this energy functional lambda to infinity. Okay, so this is reasonable, but what is the rationale behind this method? What is the geometric intuition? I think there are different ideas among different people why this method should work. In my case, I think the most reasonable one is relying upon the Faber-Kran inequality, which tells, well, it's very well known, it's 100-year-old. It tells that the first Dirichlet eigenvalue on a certain domain omega is minimal precisely when omega is an Euclidean ball. So if the up to certain technical assumption about the smoothness of the boundary. So if the boundary diverges from being just a sphere, then you pay for this perturbation and you get higher eigenvalues. So the point is that this means that when you try to minimize lambda kp, so this energy function I presented in the previous slide, so let me just show this again. So this lambda kp, when you try to minimize them, basically each subdomain tries, because of Faber-Kran, to get as close as possible to a ball. So this is some numerical analysis, some numerical simulations performed by Bergozel and Bonaï-Noël 4 years ago in the case of triangle. So you see they try to compute this minimal partitions for k equal to 2. This is the first figure, then k equal to 3, k equal to 4, k equal to 5, and so on. So you see all these subdomains try to be, in a certain sense, ball-like. This is not so easy in a case when you have sharp angles like in a square. But then you go further and further, and this pieces become smoother and smoother. Okay, and this is for p equal to 50. So as I was saying before, p is some kind of high p's are perceived as some kind of proxy for infinity, basically, which is the interesting case. Okay, so this method works because again, so Conti, Terracini, and Verzini could prove that this energy functional does have a minimum for all p and for all k, basically. The proof is variational. I won't go into it. They had to impose certain regularity assumption of the boundary, and also to explain exactly what kind of partitioning they are allowing, because basically this means that they need certain smoothness of the boundary of these k partitions. All this is in a certain sense natural, but also very technical, and it requires a lot of geometric analysis in the case of planar domains. So typically, your proofs will be variational, but you cannot really see very explicitly what are the effects of changing piece of the boundary when you try, for instance, to test new possible partitions, because your function will react in a very complicated way to changes in the boundary of partition. And this is why I like, and my co-authors like, quantum graphs, which I'll introduce soon, because everything turns back to one-dimensional case, and then it's very easy to shift partitioning points back and forth, and then still have something you can say. So we will see soon what is our setting good for. Let me just say that after this paper by Conti, Terracini, Vazzini, the story did not end. So a lot of people jumped into this topic, including Helfer and Hoffmann-Ostenhoff. Bonaí Noel was mentioned before. So a lot of people in Austria and France and Italy started working on these problems, which are very hyped at the moment. Not only this problem is well posed, but we now have, or the literature, you can find a lot of regularities, information about this partitioning problems. In particular, you know that if you have a minimum at certain partition for this functional, then this must be an equipartition. So this means that the energy, so this eigenfunction lambda 1d on each subdomain must be the same. And also, you know that this minimal energy must be an eigenvalue, and its eigenfunction will give you exactly, so the nodal domains of the associated eigenfunction will give you exactly the partition. This is in general not true, but it is true under certain geometric condition on your domain. So basically, you just draw a dual graph of your partition, and then you have to check a certain combinatorial condition on this. So a lot of nice information are known about this spectrum minimal partitions. Let me just mention at the end one very beautiful and still unanswered conjecture by Luis Caffarelli and Fan Ling from 2006. So they say that, okay, so if you have boundaries we've seen before, then at the boundary you will have very strange behavior of your nodal, of your subdomains. But if you achieve a minimal partition, then for k going to infinity, the boundary will play, of course, less and less role, and you will come up with domains which are only supported in the interior of omega, of course. And the interesting thing is that all these domains will tend to become hexagons. More precisely, the sequence LKP, so the minimal energy divided by k, will tend for k to infinity to this ratio. So lambda, so the first eigenvalue of the Laplacian with Dirichlet conditions on an hexagon of unit area divided by the area of the whole planar domain. So again, this is conjectured. This is numerically sound as a conjecture, but this is still unproved. Okay. Let's move to metric graphs, so quantum graphs, which is my topic. So what's a metric graph? A metric graph is just a graph you have studied at university, just a pair of sets, one set of vertices. We will study only finite graphs, so finitely many vertices and finitely many edges. And okay, so this is classical graph theory, but then what people decided to do a couple of decades ago is to associate every edge with an interval. And once you do so, then you come up with something that is nowadays called a metric graph. So Günther Luhmer was the first one to introduce these objects, but a lot of people, really many people in the last 30 years, or maybe now 40 years, studied these objects. And in particular, because you have now a differential structure, you can have you have these intervals, you can define a differential operator acting on the structures. You have you can have Laplaces on them, And if you have a Laplacian on a metric graph, people call this object, this construct, a quantum graph. So this is what I'm working with. Okay, and of course, so once you have a metric graph, you still can recognize the basic combinatorial structure, and this is so-called underlying graph you are depicting, you're considering. Okay, first of all, because you have a collection of intervals, then you have you can define an L2 space or Hilbert space over these objects, so just direct sum of L2 space on intervals. But of course, you don't see any combinatorics of this structure. You don't see what functions do at the vertices, at the boundary, so to say, of this interval. So in order to solve this problem, you can just introduce a space of continuous functions acting on this metric graph. So metric graph is actually a metric space, so it's the notion of continuity is very well defined. And also Sobolev spaces. Sobolev spaces are just the space of continuous function of a metric graph that are edgewise in a classical Sobolev space of order 1. So they are weakly differentiable with weak derivative in L2. Okay, what can you do with this construction? You can, first of all, you can study the spectrum of these Laplacians on these spaces. The spectrum just constructed in a very classical way, in a variational meaning. So you just take the infimum of the Rayleigh quotient, and this is perfectly well defined. There is there's much theory which has been developed about the these eigenvalues and how they depend on geometry of the graph, so called quantum graph spectral geometry. But I will not go into this. I will only present later on a very important result by Serge Nicaise in this direction, but we don't need it yet. Let me just say, so once again, lambda 1 is the lowest non-zero eigenvalue associated with the Laplacian on this quantum graph, which is in turn the self-adjoint operator associated with this quadratic form. So far so good, this classical form theory and operator theory in Hilbert spaces. Let me just add quickly that we could basically do the same also applying, so imposing a Dirichlet condition, a certain nodes of the graph. I will not go into details into this direction for the sake of simplicity of this talk, but this is also important, and this has been done in our paper too. This is in certain sense the closest case to the planar domain case I've been presenting before. But here, for simplicity, I'm just assuming that that we only deal with this variational formulation above. In particular, this means that whenever you have a vertex of degree 1, so if you cut just in the middle of an edge, for instance, or you have just one point isolated into this graph, then you will have, for this Laplacian, you will have Neumann boundary condition. So no Dirichlet, no strange boundary condition, especially on this, but just pure Neumann. Okay. Okay, so what happens if we want to partition a metric graph into K? Okay, for K equal to 2, this is, as I said before, so this is just a classical nodal approach. This has been done by Nicaise already in the 80s. He proved some kind of Chigger inequality, so you can estimate quite well what is the optimal energy of this cut. Del Pezzarossi proved something more a couple of years ago. And then for larger K, a lot of people started working on this, on the properties of nodal domains, but most of them centered in two places in the world, namely the Weizmann Institute in Israel and Texas A&M in the USA. And a lot of people collaborating with Uzis Milansky and his students, and Grigori Berkolaiko and his students obtained very nice results about nodal domains. There was also something similar to what I presented before, so Courant and Pleyel and so results. Also very recently by James Kennedy, Matthias Hovan, Martin Plum, and myself, but I will not talk about this. The point is that when you try to perform nodal domain partitioning for quantum graphs, you meet the same problem, encounter the same problems, and in case of domains. In general, a Kth eigenfunction will not have K nodal domains, but less. So you will have exactly k domains for each k only if you have a tree, so a graph without cycles, but otherwise you will definitely have less than k. You might have less than k nodal domains. So a new technique is needed, and this is where we start our investigation. So once again, the idea is to partition your quantum graph, your metric graph, into k subgraphs, which we would like to understand as clusters, just like in the discrete case. So you have these clusters G1 up to Gk, and then you associate with them an energy. Once again, either the maximum of the energies of the Laplacian restricted to the subclusters, or this kind of p norm of this sequence. And then you try to minimize these functions of all partitions. Now, in the case of graphs, it's even more unclear than for domains what is a partition. I mean, how would you like to cut your graph? And this is a very deep and important question in our theory. So I will devote a couple of slides to this. Okay, let's delve onto the simple case of this graph. This is called the Lazoo graph. So it's just a graph consisting of 3 vertices and 3 edges. And the question is, what is a natural way of cutting into this, to cut this object into 2, for instance? Okay, what these people I was mentioned before, so Berkolai, Konsmilansky, and their students were doing was to just restrict to the case where partitions are obtained by cutting into the interior of an interval, like in these 2 cases I'm presenting here. This is good. You don't have to run into the problems given if you have to cut through a vertex. The point is that, of course, if you want to apply continuity methods and variational methods, this is very unstable, because it's, I mean, if you just if an edge gets a bit longer, then you might have to cut closer and closer to a vertex, and then at a certain point you will be forced to cut into a vertex. And to avoid these problems, Berkolai, Konsmilansky, and co., they had to impose certain geometric conditions on the graphs, which had to guarantee that eigenfunctions never vanish in the vertices. Again, it is meaningful and works well, but it is very strong restriction on the generality of graphs you're considering. So this is what we wanted to get rid of. And so we came up with 2 different notions of partitions, which we call rigid and connected partitions. So rigid partition is a partition where you are allowed to cut through vertices, and then when you cut through a vertex, then you also allowed to, so you may or may not decide to also tear apart the vertices in the cluster that arises. So for instance, on the right now, you see, so we've cut our Lazoo graph into 2, and because we are cutting through the vertex in the middle, then we can decide what to do with these 2 new vertices that arise on the right. We could keep them together and then get some circle, some loop on the right, but we'd also are allowed to cut them into 2. And another even more general way of cutting would be to allow to cut just everywhere within a cluster. So not only where you divide a cluster from another cluster, but also in the middle of a cluster in a certain sense. Well, as long as clusters stay connected, because this is a very minimal assumption, very reasonable one. Okay, so let me just summarize. Connected partitions in a certain sense are most general we can come up with, at least we can think of at the moment with my co-authors. Rigid partitions are definitely better behaved. In a certain sense, they're closer to what Berkolai, Konsmilansky, and co. were doing, but they have they have more restrictive conditions. So let me just show an example of a non-connected partition. So this is what happens if you allow also them to be non-connected. But this, we will not consider this kind of partitions at the moment. So what we could prove in this paper, which was just accepted in calculus variations, is that for each k and each p, you actually have a minimal partition. So connected partition that minimizes this energy lambda k p. So in general, you have a minimal partition, which is a connected partition, but this need not be rigid. However, you can restrict this energy functional to the class of rigid partitions, and even this restriction will have a minimum, which of course this will be rigid. So you can just, depending on the problem you're considering, you can decide whether you want to have larger generality, lower energies, but only at the price of only having a connected partition. So you can basically destroy a lot of the topology of the original graph, or you want to get clusters which closer resemble the original topology, but more restrictive object. Both of them are nice. The important or interesting point is that this restriction of this energy function does not in general have minimum on the class of proper partition, which was this restriction, these partitions considered by Berkolakos, Milansky and co, where you can only cut in the middle of a vertex. This really shows that if you want to go variational, then you need to allow for this more general notions of partitions. Okay, so the minimum P star C or P star R of this energy functionals will deliver two energies, which we denote in this way. So capital L C and capital L R, and they will be called minimal connected energy and minimal rigid energy. And of course, you always have your parameters K and P with you. So you know that there exists a minimal partition. You also know that there are, in certain sense, as I will show, the proof is constructive, but still it's not easy to find one minimal partition. So it's nice to have certain sufficient condition to recognize minimal partition. One is the following. So if you have a rigid partition whose energy is exactly given by the energy of one interval of the kth length of the whole graph, then this is actually a minimizer of this energy. So if you can come up with the partitioning of your graph where each of the k pieces is an interval, then you certainly have an optimal, minimal energy. But this is not always possible. So the question is what happens in the other cases. I will show a couple of examples right away. Let me mention that unlike in the case of planar domains, in general, a minimizer, a minimizer of the energy functional need not be an equipartition. So again, so this opens the quest for general partitionings. So let me show a couple of nice pictures of examples. So let's start with this very simple graph. So it's a graph consisting of 2 vertices and 3 edges, what we call the tree pumpkin. So what would be a minimal 2 partition of this? Well, you can think you could just cut in the middle of this pumpkin and get also two half pumpkins, so maybe 2 half cucumbers. But this is not minimal, so you can come up with a better option, which is represented here. So this is maybe an unusual way of cutting through a graph like this, but you can check the definition and you can see that this is a rigid partition. So this is not proper in the sense of Berkolakos Milansky, but it's still rigid. So still the better of our 2 classes of partitioning. And because you come up with 2 intervals, each of them the half of the size of the graph, this is in fact even, I mean, you can be, this is guaranteed a minimizer. Once again, you have this strange graph here. What is the best way of cutting into this? Okay, now, once again, you could think the best way would be to cut in the middle, but this is, again, not the best way of cutting, of partitioning. These 2 graphs I've drawn on the bottom, they are both minimizers. Interestingly, they deliver the same energy, but you will see one of them, so the one on the left is a rigid partition, and the one on the right is a connected partition, so a slightly more general one. So it could be that you have, so this already shows that your energy will have a minimizer, but this minimizer need not be unique, and need not even be unique in the same class. Once again, a 6 pumpkin, what is the best way to partition this into 2? Well, this is the best way. So as you see, something maybe unexpected may happen. It's up to you to decide whether this is a natural way or not to partition through graphs. But for sure, this is a guarantee to return you exactly k pieces if you go for higher k than 2. Last example, a dumbbell. So you see that you could have that you have different minimizers for connected and rigid. So the left on the bottom is a rigid rigid minimal partition, and the one on the right is a connected minimal energy. Okay, let me just present a couple of qualitative properties of this minimal partition. So once again, let me recall some notation which I introduced already before. So capital LC is the minimal connected energy, and capital LR is the minimal rigid energy for parameters k and p. So once again, so you take your energy functional lambda and you restrict it to the class of connected or of rigid function. Then of course, in either case, we get a minimizer. This is the minimal energy. So what can you say about this dependence? So the dependence of these objects on the parameters k and p. So first of all, you can see that the connected minimal energy is monotonally increasing in p. And I will show you in a few minutes that this is a very simple but also very mighty tiny lemma because it simplifies a couple of proofs in different contexts. So what about the increasing, I mean, the monotony in k? So this means, let me be more explicit. If you partition into 2 or into 3 pieces, can you expect that the 3 partition, the 3 minimal energy is higher than the 2 minimal energy? Well, you would expect so, because if you think that you can partition into 2 intervals or 3 intervals, the 3 intervals will be shorter, so the energy should be higher. It turns out that the connected minimal energy is actually monotonally increasing in k, but remarkably, we do not know if this is the same for the rigid energy. So for the rigid energy, we only know that this minimal energy is eventually monotonically increasing. So for large k, then you have that at a certain time, a certain point, things get normal, so to say. So you actually find that if you find a partition in k+1 domains, then your new energy will be higher. But for low k, this is remarkably not the case, because you can have strange phenomena related to loops, basically. Okay, there is in our paper, we will find a conjecture which would settle the problem, but this conjecture is still open. So again, it's a strange, bit spooky issue for this theory. Okay, this is just I will not go really into this slide, but I just want to tell you that even though p less than infinity is just considered as a proxy for p equal to infinity in our setting, actually interesting thing can happen for so smaller p's, because not only the energy but even the partition itself might depend on p. So it could come up with different geometric interpretation of minimal partitions depending whether you consider p equal to 1 or maybe 7 or infinity. So basically, you can play with parameter p to get better behaved partitions depending on what you are looking for. So this the proof is just based on an implicit function theorem, basically. Okay. Also, in the case, unlike in the case of domains, you do not need to have equipartition. So let me just make a nice interaction as an interactive moment of this talk. So let's assume you have a figure 8 graph like this, with one edge very short and the other very long. Then it turns out that the minimal rigid partition of this graph would be just something like this. And of course, this is not an equipartition. So this is a remarkable difference from the case of domains that might or might not be inviting you to study this kind of problems on domains, on graphs rather than domains. Okay, let me just, before, my time is almost up, so let me just say some words about the proof, which is actually the most interesting part of this method, I'd say. The proof is based on a actual topological idea. So the idea is how to metrize, in a certain sense, the space of allowed, of admissible partitions. So first of all, let us denote by gamma G the space of all metric graphs whose underlying discrete graph, so this combinatorial basic structure of a metric graph is given by G. So so here I use capital G as a discrete graph or a combinatorial graph, and this mathcal G is the metric graph. Okay, so of course, so once you fix the basic combinatorics of a certain discrete graph, then on the set of all metric graphs constructed over it, the only thing that determines the metric graph is the vector of edge lengths. So in particular, once you fix the discrete graph, then on all metric graphs on top of it, you can measure the distance just by measuring the distance of these vectors of lengths in a Euclidean space, in the space of the dimension of the number of edges. Okay, so this is a nice matrix space. The only problem is it's not complete. So you just close it up and you take this completion gamma G bar. So once you have, so this fixes the space of all graphs, metric graphs constructed over certain discrete graph. And now we want to take a whole metric graph, our ambient metric graph, cut into k pieces, and all what's appearing there will be k different metric graphs on two different discrete graphs, and we want to compare them again. So on the first tiny discrete graph, we can measure how different our subgraphs are. On the second one, again and again, and we want to compare all them together. So we want to patch all this tiny metric graphs associated with each subgraph together. So what we do is we introduce a notion of similarity between two connected partitions. So we say that two partitions are similar if they can be identified up to shifting separation points between subgraphs along edges interiors. So it's easy to see that this is an equivalence relation, and so basically two partitions within the same equivalence class necessarily have to share the same underlying discrete graph. So what we do to measure the distance between two partitions is to take the sum over the distance between the corresponding subgraphs over all spaces induced by the same discrete underlying graph. So once again, you have your partition into k pieces. For the first piece, the two subgraphs, the two clusters, must share the same discrete underlying graph. So you measure the distance in Euclidean sense on that for the first underlying discrete graph. Then you do the same for the second, the third, and so on up to k, and then you sum up all together, and then you get a well-defined notion of distance between partitions. So this, once again, is an incomplete metric space with respect to this distance. You close it up and you get so complete metric space. This is CK bar. The point is that upon closing it up, you could have to include also partitions which are not into k pieces, but into m pieces for some m smaller than k. So this is a problem because we started this whole method for the main purpose of having exactly k pieces in your partition. The good thing is that the set of rigid k partitions is closed in SU2CK, so we will have some good behavior if we study continuous function over this metric space. But we still have to fix this idea with the with the number of clusters in your partitions. Okay, what we can prove is the following. So this was the main tool we had in our paper. This is a purely variational theorem. So assume you have a lower semi-continuous functional J. Okay, technically it has to be slightly stronger than this, so-called strongly lower semi-continuous, but I will not go into detail. You define it on a certain set A of partitions, which has to be at least contained to this closed metric space of connected partitions or its closure. Then you can see that this actually attains a minimum. So you have a minimizer of this functional J, both restricted to connected partitions and its restriction to rigid partitions. And additionally, okay, so again, so this minimizer could be also an M partition for M less than K, but if you impose another further condition, this is some kind of coercivity condition, then you can see that your partition will consist of K clusters. So what does this coercivity mean? So if the size of clusters goes to 0, then the energy have to explode. So basically, this means that your functional can only attain its minimizer in the interior of your set of partitions. So where your partitions are actually into K clusters until to less than K clusters. Okay, so what does this abstract theorem say about our original problem? The point is that, of course, you can define J to be the any of this spectral minimal functional we were having at the beginning. So this capital lambda Kp. And this coercivity condition is actually satisfied because Serge Nicaise proved in the 80s that you have this very nice isoperimetric inequality. So the lowest non-zero eigenvalue of the quantum graph Laplacian can be estimated from below by the size of, or 1 over the size of the graph square times pi square. So if your clusters tend to have size going to 0, then your energy will certainly explode. So you're guaranteed to attain, I mean, your functional is guaranteed to attain its minimizer in the middle of the partition set, and therefore you can also have actually K clusters instead of less than K clusters. Okay, let me devote the last 2 slides to this follow-up paper was mentioned at the very beginning. So what happens to these energies? What can we say about these energies? First of all, because the set of rigid partitions is smaller than the set of connected partitions, when you minimize a function of a smaller set, of course, your minimum will be larger in general. So you have that the connected minimal energy will be less or equal than the rigid minimal energy. So this is just clear. What we can see is a nice 2-sided estimates for these energies. This is the main results of our paper, so my paper with Matthias Hoffmann, James Kennedy, and Marvin Plumer. So the estimate from below is similar to the one I showed before by Serge Nicaise. It's just so the kth minimal energy is just K squared times this lower Nicaise bound, so pi square over G square. And on top, it's even more interesting because you also add a bit of geometric or maybe combinatoric information about the problem. So you have a correcting term given by the number of edges minus 1. So in case of a graph with a lot of loops, this term will be significant, and then you will have a large deviation from the pi square over G square behavior. So let me mention that the upper bound holds for large K, the lower bound only for K, so for all Ks. And interestingly, the lower bound is attained if and only if, so it can be identity can be characterized if and only if every cluster is precisely interval of length G over K. So it's a so homogeneous partitioning of the graph in a certain sense. In particular, in this case, we do recover, just in the case of domains, that minimal partitions are equipartitions. Also, we know that in general this is not the case. two words about the proof. The lower bound is proved for p equal to 1, and then you apply once again this Nicaise isoparametric inequality, and then just standard application of Jensen's inequality. And the upper bound, here we use the monotonicity of these energy functional in p. We can just take p equal to infinity, and then we use our variational structure. In this sense, we can just apply test partition argument. So you find we find explicitly, construct explicitly partition which attains the energy given on the right. So this pi square over g squared times k plus e minus 1 squared. And so we know that the minimizer must have energy which is less than that. So we are done with the proof. In particular, the interesting point of this two-sided estimates is that both upper and lower bounds converge for k equal to infinity. So we have this asymptotics here. So both the minimal and the connected and the rigid energy divided by k square converge for k to infinity to pi square over, L square should be the size of g. So g square, what was g square in the previous slide. And this means that the partitions tend to consist of a few pieces around vertices of the original graph, which will be stars, plus the large majority of the clusters will be just intervals, all of them of the same size, namely of the size size of the total graph divided by k. So in a certain sense, you may or may not be invited to think this is a counterpart of the Caffarelli-Lin hexagonal conjecture for quantum graphs. So in particular, this means that not only the eigenvalues of a quantum graph satisfy Weyl asymptotics, this was already known for many years, but also this minimal energies, minimal partition energies. This is something which is remarkably still unknown in the case of domains. So this shows that quantum graphs are a very nice, okay, maybe you can call it a sandbox, but certainly it's an environment where you can prove more and different things than in the case of domains. So a lot of results that would require a lot of technical geometric arguments in the case of domains can be reached in a certain sense more easily in the case of metric graphs. So this is also, my talk is also an invitation to you, if you don't know how to proceed in case of problems on domains, to go lower dimensional, to first try to assess things on metric graphs and then try to understand what happens there, and maybe you can develop some ideas that can be also exported to the general case. Okay, this is pretty much what I wanted to say, and thank you for your attention.
Okay, thanks Delio for the talk. I don't know if someone wants to do some questions. Now is the time for questions. Luciano, say yes.
Okay, Delio, I would like to ask you a simple question. And the assumptions that you have put on the operator, is that this is a Laplacian on your graph, or is a positive operator? Is a more general operator than the Laplacian, or the operator who defines the functionals?
Okay, so in our paper we were mostly motivated by the Laplacian, but again, this variational result that was mentioned about the functional J, this is very general. So it's only, you only need one one lower semi-continuous function. So in fact, in our paper, we use this generality to attack different problems. We were rather interested in different functions of eigenvalues. So the main operator was still the Laplacian, but we were studying different combinations. For instance, instead of taking the minimum of the infinity norm, we were considering some kind of maximal energy or something like this. But as soon as you have okay, I'm trying to be bold. I'm not. I think it is. I think I'm right. Only thing you need basically is this coercivity assumption. So this lowest May continuity will certainly go through also for different operators.
Okay.
The only thing that you have to make sure is that when your clusters go to 0, then the energy will explode. And this will probably also work for different like Schrödinger operators or Laplacians with different vertex conditions. What happens for non-elliptic operators, I don't know. It would be interesting. With Federica Gregori from Salerno, I'm starting working on B-Laplacian partitioning.
Oh.
This is even a bit more complicated because the lowest eigenfunction need not be strictly positive. So you can have some sign changes even on the very bottom of the spectrum, but this I don't know. So I think what we did was for Laplacian. What we probably might easily do is also for Schrödinger operators, and for the rest, it's open.
Okay. Okay. Thank you.
Okay. If there is no more question, someone. Oh. Okay. If not, I think we are going to thanks to Delio the talk up again. I'm going to give my thanks, and now I think we are going to do a stop for 5 minutes or something like this, and the next speaker will be Jan, but we will start in 5 minutes, okay? And in this way, everyone can go to take a coffee, or I don't know, or go to do another thing. So we continue in around 5 minutes. I am going to stop the recording, okay?